In this video, we will talk about the relationship between electric field lines and electric flux and the idea of Gauss's law. Electric flux is a way of counting the number of field lines that pierce through an area. In this example, we see that the field lines are piercing through the square of area A. Let's be clear about what we mean by piercing through. If I put a cube like this in a uniform electric field, which is pointing to the right, then this face of the cube will have a lot of field lines piercing through it. But this face of the cube will only have field lines passing tangent to the face. None of the field lines will actually pierce through it. They will not go perpendicular to the surface. They will only pass tangent to the surface. Similarly, this face again has only field lines passing tangent to the surface and not perpendicular to it. Here again is another illustration of field lines piercing through a surface. Let's consider a positive charge. Since it is positive, it has field lines that radiate away from it in all directions. Supposing we want to look at the flux passing through this surface. Now, what I've shown here is actually a surface, but we're viewing it from above, so it just looks like a line. You can imagine it as a sheet of paper being placed there, and we're looking at the number of field lines, or toothpicks if you like, piercing through it. Flux is a scalar quantity and can be positive, negative, or zero. So how do we decide if the number of field lines passing through a given area, if that number is positive, negative, or zero? To do that, we need to first introduce the concept of an area vector. For every surface with a certain area, we can associate a corresponding vector. This is called the area vector. This vector points perpendicular to the surface. So here we have a flat square, and perpendicular to that square is the area vector. It doesn't have to be a square. It could be a circle, a disk, that is. Right? A surface. It always has to be a surface. So it could be a disk, some arbitrary shaped surface like this, or something nice and regular like a square or rectangle. And in each case, we see that the area vector is perpendicular to the surface. It is normal to the surface. But if I look at a surface, I notice that it actually has two normals. I could point this way, or I could point this way. How do I pick? In fact, there is no difference. Both are equally valid. So you can pick either of the two perpendiculars to a surface. Let me again make 2 points about the area vector. It is perpendicular to the surface. This black arrow is tangent to the surface, but the area vector is perpendicular to the surface. So there's a 90-degree angle between the tangent and the area vector. And the other is that the size of the area vector depends on the area of that surface. So if you have a bigger area, you have a bigger arrow. If you have a curved surface, you divide it into little areas, dA. And for each of those little areas, if they're small enough, they look almost flat, and you can define a perpendicular to that surface, a normal to that surface. And that will be a little area vector, dA. This means that with a curved surface, at each different point, you can define a normal, right? All these vectors are perpendicular to this curved surface, and each of them accounts for a small bit of area around it. This is how we treat curved surfaces. Again, though, remember that there are actually two choices. We could do all these vectors pointing like this, or we could do them all pointing towards the inside of the curve. However, once we come up with a closed surface, such as a sphere or a cube, what I mean by a closed surface is a surface that encloses some volume. Okay? In that case, we always pick our area vectors pointing outward. Again, there will be lots of different area vectors at different points, but for a sphere, for example, as shown here, all these area vectors are pointing outward. Whereas for an open surface, which does not enclose volume, you can choose either one of these two normal vectors. Once again, a closed surface is a surface that encloses a volume. There is a clearly defined inside and outside. And we always pick our normal vectors, our area vectors, so that they point from the inside to the outside. But with an open surface where there is no clear inside or outside, even if it's curved, as long as it does not enclose a volume, then we can pick either one of the two normals to be our direction of the area vector. Now that we have this idea, let's return to our example. This is, say, a piece of paper that we've put, and the field lines are piercing through it. And now I've chosen this red arrow to be my area vector representing the area of this piece of paper. If the field lines are pointing in the same direction as the area vector, roughly, then we can say that the flux is positive. If they point in opposite directions, then we say that the sign is negative. And if the field lines do not pierce the surface, if they are simply tangent to the surface, then they will be perpendicular to the area vector. Notice that because the area vector is normal to the surface, if the field lines are perpendicular to the area vector, they are tangent to the surface. Well, in this case, since they are not piercing through the surface, the flux is zero. Supposing now I take a positive charge and surround it by a sphere. Since I'm looking at it in cross-section, you only see a circle, but imagine that this charge is enclosed by a sphere. What is the sign of the flux? Well, since the sphere is a closed surface, we know that the area vectors are always pointing outward. And in this case, the field lines are also going in the same direction. Since they're going in the same direction, the flux is positive. And we can see that in this case it is positive everywhere. So we have a positive flux for our positive charge. What if I have a negative charge? I surround it by another sphere. But remember, the area vectors are still pointing outward. And so the area vectors are now pointing in the opposite direction to the field lines. And so the flux associated to this electric field and this sphere is negative, just like our negative charge. Now, the sphere, or whatever shape you choose, doesn't have to be centered on the charge. We can choose an oblong egg shape and put it around the charge like this. And we see that we still have a positive flux. The normals are pointing outward, and so are the field lines. We also notice that the number of field lines passing through the surface is still the same. You can count and check that there are 24 field lines passing through this egg shape, just like there were 24 field lines passing through the sphere earlier. And again, it doesn't have to be a smooth shape. It can be any arbitrary shape like this. And if you count, you can see again that there are 24 field lines passing through this surface. So let's examine this. What if we have two shapes surrounding our charge? Which one has more flux passing through it? Remember, flux is simply a way of counting the field lines. So what we find is that in this case, it doesn't matter about the shape or the position or the size. The number of field lines passing through this green egg shape and this red sphere are both the same. They each have 24 field lines passing through and all going in the outward direction. So they have the same amount of positive flux. What about this case? Now, which one, red or green, has a greater amount of flux? Pause and think about this for a moment. Let's now discuss. Again, if we count, we see that each of them has 24 field lines passing through. And so they each have the same amount of flux. And curiously, they each enclose the same amount of charge. What about this surface? Here we see that there are 4 field lines entering and going in roughly the opposite direction to the area vector. Remember, the area vectors for a closed surface always point outward. So we see 4 field lines entering in roughly the opposite direction to the area vector, which counts as a negative flux. But we also have 4 field lines exiting in roughly the same direction as the area vector, which counts as a positive flux. Since we have 4 field lines entering and 4 field lines exiting, the total amount of flux for this entire surface is 0. Take a moment to wrap your mind around that. Since the number of field lines entering is equal to the number of field lines exiting, the amount of negative flux is equal to the amount of positive flux in magnitude. And so the total amount of flux for this closed surface is 0. And how much charge is inside that surface? How much charge is enclosed in the inside volume? 0. Let's look at this. Here we have this green oblong egg shape. We have a red hexagonal shape. Again, these are supposed to be closed volumes. They're just shown in cross-section. And we have this green triangular, which would be a prism shape in 3D. And let's look at the flux. Here the charge is negative. And for both the green oblong and the red hexagon, we see that the field lines point in roughly the opposite direction to the area vector normals. And so they both have negative flux and they have the same amount of negative flux. 24 field lines entering, none exiting. Whereas this blue triangle has the same number of field lines entering as exiting. And so the total flux for this entire blue triangle is 0. Wait a moment, you might say, what about this line? This line is only exiting, it's not entering. Well, that's simply because I haven't drawn out the field lines completely. Remember that field lines can't start in the middle of nowhere. They have to start at a positive charge and end on a negative charge, or they need to go off to infinity or come from infinity. So all that's happened here is that I simply haven't drawn the field line in completeness. It's actually still extending outward like this, and we see that we have the same number of field lines entering and exiting, and so the total amount of flux for the blue triangle is 0. So now we have an idea of what Gauss's law is about. It's about relating the number of field lines passing through a surface, passing through a closed surface that is, to the amount of charge enclosed. Here we see that both the green surface and the red surface enclose the same amount of negative charge, and they both have the same amount of negative flux. The blue surface encloses no charge, and so the total flux passing through it is 0. Let's test this idea further in a more complicated situation where we have more than one charge. For example, let's look at a dipole. Here we have a dipole with some of the field lines shown. Now, if I enclose the positive charge by this red oblong shape, we see that it has field lines pointing outward in roughly the same direction as the area vectors, and so that counts as a positive flux. And indeed, we are only enclosing a positive charge. The presence of the negative charge here bends the field lines, but does not change the total amount of flux, which is only related to the amount of charge enclosed. What if I choose this shape? Now we have both the charges inside, and so the total amount of charge, since there are equal amounts of positive and negative charge, the total amount of charge inside the volume is 0. But look, we have flux. But how much flux in total? In fact, if we count carefully, we see that the total amount of flux is 0. All these blue lines represent field lines which are entering the surface in roughly the opposite direction to the area vectors. And so we have a negative flux on this side. All these field lines represent field lines which are exiting the surface in roughly the same direction as the area vectors which point outward. And so these represent positive flux. If we count, and feel free to pause the video and check for yourself, we find that there are 14 field lines entering and 14 field lines exiting. Since the number of field lines entering and exiting are the same, the total amount of flux is 0, which corresponds with our total enclosed charge of 0. So now we come to the statement of Gauss's law. This is what it looks like mathematically. And in the next video, we will unpack exactly what all these terms mean. But first, let's put it in words. The total electric flux, which is represented by this symbol, phi sub E, E for electric, passing through a closed surface S. So this is the electric flux, which can only be evaluated using a surface. And so we are evaluating the electric flux on a closed surface S. This expression is equal to the charge enclosed, Q enclosed by the surface S, and divided by the constant epsilon naught. That is the statement of Gauss's law. Let me make one more point. electric flux can be defined for any surface, whether open or closed. You simply need to define the area vector of the surface and see if the field lines point in roughly the same direction, on the opposite direction, or are perpendicular to the area vector. But you can only use Gauss's law with a closed surface. This can be any type of closed surface. It could be a cube, a sphere, a cylinder, anything that encloses a clearly defined inside and excludes the outside. So there's an inside volume and an outside volume. If you have such a surface, such a closed surface, you can apply Gauss's law to it and look at the electric flux passing through that surface and relate it to the charge enclosed by that surface. That's all in this video. We will continue in another.